Hello. We're going to do some examples for the binomial probability distribution. So the first example says that the probability of success of an experiment is 0.65. So we have p equals 0.65. If the experiment is conducted 10 times, that means that this is going to be done 10 times. We have 10 trials. So for example, this might be that we're flipping 10 coins with a weighted coin of probability of success of 0.65. So we have n equals 10 total trials. And as a reminder, based on our assumptions from our probability, this n is fixed, meaning now that we've claimed that we have 10 trials, we're doing 10 trials, and if we were to change it, we would actually be using a different binomial distribution. This probability of success is also fixed, so p is equal to 0.65. Now, while we're here, we actually could also write down our probability of failure. So if you remember, q is equal to 1 minus p, which is equal to 1 minus 0.65, giving us a probability of failure of 0.35. Now, I'm writing this here because this is going to be for the next couple examples. Now, the question asks, what is the probability of getting exactly 6 successes? So in this case, we're looking for the probability that our random variable x, which is the number of successes, is equal to 6. Now, if you remember, our probability of success for a binomial probability is the probability that x equals some r is equal to n choose r p to the r power 1 minus p, or q, to the n minus r power. So whenever you have a problem like this, we want to know the probability of exactly 6. Well, remember, exactly is another way of saying equals to. So we're looking for the probability x equals 6. Or you could write it, if you wanted to, just as the probability of 6. So to do this, we're going to use our formula, and we're going to plug in the values we have. So we have n choose r. Well, in this case, n is 10. It's the number of trials that we're doing, right? It's like we're flipping 10 coins. R is our number of successes, 6. So we're going to do 10 choose 6. Now we have p, which is 0.65, to the r power. R is 6. Then we have 1 minus p, or q, which is 0.35, to the n minus r power. So I'm just going to write it as 10 minus 6 power, which is to the 4th power. So doing this, we're going to actually find that the answer is equal to 0.2377. Now, just as a reminder, if you were doing this calculation, you didn't remember how to do the combination, this would end up being 10 factorial divided by 10 minus 6 factorial, 6 factorial. So 10 minus 6 is going to give us 4. So 4 factorial, if you remember the trick to do it by hand, you're going to leave the bigger factorial. In this case, it's the 6 factorial. And then you're going to write out the smaller factorial. In this case, it's 4. So this is going to be 4 times 3 times 2. And you don't have to put the 1, because even though it's times 1, the 1 doesn't change anything. Then for your numerator, you're just going to go 10 times 9 times 8 times 7 times 6 factorial. You do it until you get to the bigger factorial in the denominator. Cancel those out. And then we can do some cancellation with the rest of these terms. So for example, this 3 will cancel out part of that 9, leaving us with 3. And then this 2 and 4, we can cancel those out with the 8. So we get 10 times 3 times 7, or 210. There's 210 ways that we can get 6 successes if we are doing 10 trials. And then the probability of getting 6 successes is 0.65 to the 6th power. The probability of getting 4 failures is 0.35 to the 4th power. Put all that together, and you get the total probability of getting exactly 6 successes of 0.2377. So the next problem is, what is the probability of getting no successes? So if we're saying no successes, in this case, this is telling us that we want the probability of getting 0. So we're going to set the problem up exactly the same way. It's going to be 10 choose 0, 0.65 to the 0 power, 0.35 to the 10 minus 0 power, or to the 10th power. Now, anytime you are doing a probability where it is all successes or no successes, it actually becomes really easy to calculate. Because if you remember from when we were doing our combinations, anything choose 0 is always equal to 1, right? If I have 10 trials, how many ways can I get none of them as a success? Well, only one of them, all failures. So this term is going to go to 1. Any value that's not 0 to the 0 power is going to be equal to 1. And then really, this is all you're finding, 0.35 to the 10th power, which is a very small number. It is pretty small. It's 0.00003, which depending on where you're rounding, you might say that this is almost 0. What about if we wanted the probability of getting all successes? So same thing this time. In this case, if all of our outcomes are a success, that means if we did 10 trials, that means we have 10 successes. So writing this out using our binomial distribution formula, this is going to be 10, choose 10, 0.65 to the number of successes, so to the 10th power, 0.35 to the 0 power. So again, if I have 10 trials, and I'm asking you how many ways can I get all successes? Again, the answer is only 1, right? All of them are successful. So this term, of course, also goes to 1. 0.35 to the 0 power goes to 1, meaning that all we have to calculate is 0.65 to the 10th power, which will give us 0.0135. For our next problem, it asks, what is the probability of getting at least 6 successes out of our 10 trials? So if you remember, at least means greater than or equal to 6. So what we're actually looking for is what is the probability that my random variable x is greater than or equal to 6. Now, the thing is, when you have a problem like this, notice our binomial probability doesn't give us the ability to find the probability of a set of outcomes. It's just a single outcome. So what we actually have to do is we have to break this down into simpler statements that are single outcomes. So this would be the same thing as saying, what is the probability that I get 6 successes plus the probability that I get 7 successes plus the probability that I get 8 successes, plus the probability that I get 9 successes, plus the probability that I get 10 successes. And then we're going to set this up exactly the same way, but we're going to do it for each of these. So the first one is going to be 10 choose 6, 0.65 to the 6th power, 0.35 to the 4th power, plus 10 choose 7, 0.65 to the 7th power, 0.35 to the 3rd power, plus 10 choose 8, 0.65 to the 8th power, 0.35 squared, plus 10 choose 9, 0.65 to the 9th, 0.35 to the 1st power, and then plus 10 choose 10, 0.65 to the 10th power, 0.35 to the 0 power. So now, to solve this, one thing I want to point out very quickly is we actually already found the probability of getting exactly 6. If we were to go back to our first problem that we did, we had that the probability of getting exactly 6 successes was 0.2377. So no reason to recalculate that. We also looked at what is the probability of getting all successes, which is this one, which we said was really easy if you want to calculate it, because this term is going to go to 1, this term is going to go to 1, and you would just get 0.65 to the 10th power, which is going to be equal to 0.0135. So really all we have to find is the probability of getting 7, 8, or 9 successes. Now, what I'm going to do is I actually want to work backwards, because this is actually the easiest one for us to find. Because 10 choose 9, if you remember from when we were doing combinations, anything choose 1 or anything choose n minus 1 is going to be equal to n. So n choose n minus 1, well, 9 is 1 less than 10. This is going to be equal to n, which is our 10. So this term is going to be 10. The 0.35 is to the 1st power, which means it's just 0.35. So all you're doing is you're figuring out what 0.65 is to the 9th power, multiplying that by 0.35, multiplying that by 10. And then basically we would have to do this calculation for each of these. So if we look at the slides here, we'll get some values for each of these, and in total we'll get a probability of 0.7515. What about if we asked, what is the probability of getting at most 5 successes? So at most means less than or equal to. So in this case, we're looking at the probability that x is less than or equal to 5. Now, you could find this by saying, okay, well, this is going to be the probability of getting 0 successes plus the probability of getting 1 success plus the probability of getting 2 successes plus the probability of getting 3 successes plus the probability of getting 4 successes plus the probability of 5 successes. So we could do this, and this is perfectly valid, right? You could plug in 10 choose 0, 0.65 to the 0 power, 0.35 to the 10th power. You could do it for probability, for 1 success. You could do it for 2 successes, 3 successes, 4 successes, 5 successes. But what I actually am going to do is I'm going to use a trick because of the fact that what do I know about my discrete probability distribution? All of the probabilities must sum up to 1. Well, if we look at all these probabilities, probability of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the probabilities from 0 to 10 account for all of the probabilities. So if you actually notice, this is everything that was not included in this prior example, meaning that I could actually rewrite this probability. Instead of being probability of 0, 1, 2, 3, 4, and 5, this is the same thing as saying 1 minus the probability that x is greater than 5, right? Because not less than or equal to 5 would be something that is greater than 5. But remember we talked about when we were talking about discrete probability distributions. This is the same thing as saying 1 minus the probability x is greater than or equal to 6. Well, we actually already have that value. Probability of x greater than or equal to 6 is 0.7515. So then I just have to put 1 minus 0.7515, which would give me 0.2485. If you look at the slide, that is exactly what it is. And I actually didn't have the slide up when we did this. And notice I didn't even need to use a calculator. I cheated on this one because I just looked up the answer. But on this one, I was able to do that without a calculator or anything. So this is one thing to keep track of. Sometimes when you get problems where it looks like a lot of calculations, look at if you can sometimes find the complement of it and then subtract that from 1. So just as a really quick example, let's say that you had n equals 20. And I asked you to find the probability that x is greater than or equal to 2. Well, in that case, you'd be looking for the probability of 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. Or you could say everything except the probability of 0 and 1. This would be a lot easier to find. 1 minus the probability x is less than 2, which would just be 1 minus the probability of 0 plus the probability of 1. So this is actually one of the strengths of the fact that with a probability distribution, all of your probabilities must sum up to 1, which means that if you have a really big calculation in one direction, you might actually have a very simple calculation just by using the complement of this. Our next example asks us to find what is the probability that we get more than 7 successes, but at most 9 successes. So if you kind of think about this, if we were to draw out all of our possibilities, I'm going to do this as a number line, but the first one is asking us for more than 7 successes. So I'll start this at like 6, 7, 8, 9, 10. And the first one wants more than 7. So if we were to draw all of our possibilities, it's everything greater than 7, but not including 7. The second part is that it is at most 9 successes. So this would be, so this first one was greater than 7. This next one is less than or equal to 9. So this would be a square bracket and then everything to the left. Now this can be thought of as an and statement because anytime you have a probability that must be this and also this. So it has to be greater than 7 and also less than or equal to 9. Meaning that focusing on the first one, So actually, let's write it down real quick. We have the probability that 7 is less than x is less than or equal to 9. Well, remember with discrete probabilities, anytime you have greater than or less than, to actually figure out what we're actually solving for, we're going to change this in terms of a greater than or equal to or less than or equal to. So the fact is that 7's not included in this and nothing is in between this. It's actually going to be everything greater than or equal to 8. So the values that we're looking for are the values between here and here, which gives us what? Probability that 8 is less than or equal to x is less than or equal to 9 is just equal to the probability of getting an 8 plus the probability of getting a 9. So whenever you have an interval of discrete probabilities, first of all, you probably want to get it in terms of greater than or equal to or less than or equal to. And then once you have it in terms of that, you just have to figure out what values fall between those values, including them, because you've turned it into in terms of or equal to. And this is just the probability of 8 plus probability of 9. So plugging in our probability into our probability distribution for binomial, this is just going to be 10 choose 8, 0.65 to the 8th power, 0.35 squared, plus 10 choose 9, 0.65 to the 9th, 0.35 to the 1. Which remember, this is going to be just equal to 10. This is just going to be equal to 0.35. So this one's pretty easy to calculate. This is really the only one that you have to put any effort into. For the next example, we're actually changing up the scenario a little bit. In this case, suppose that a company owns 400 computers. Each computer has an 8% probability of not working. And suppose that we randomly select 20 computers. So for this problem, you see that you have two possible sizes for your trials. Well, it's not the 400 computers, because what we're doing is we're actually using a sampling technique to select 20 of the computers. These are the ones we're actually going to be testing. So we have an N of 20. And our probability of success is 8%. Now, of course, to do these calculations, though, we need to convert that to a decimal. So if you have, for example, that P is equal to 8%, right? You can kind of think of like 8.0. To put it into decimal form, you need to move over to the left 2. And the fact that there's no 0 here, you would have to add it. So this is going to be equal to 0.08 for our probability of success. So now what I'm going to do is I'm actually just going to quickly write down what is my probability of failure while we're here. So my probability of success is 0.08. 1 minus 0.08 gives me my probability of failure of 0.92. Now let's actually do some calculations for this. What is the probability that 5 will not work? Okay, so now here's the thing you have to be very careful about with a problem like this. What does P, our probability of success, represent? If you read the problem, it says each computer has an 8% or 0.08 probability of not working. So this is the probability of not working. So the first problem asks us, what is the probability that 5 will not work? Meaning that this is our probability of success. Our success condition is finding computers that do not work. So we're just going to do probability of finding a 5 or 5 computers that don't work. And this will be 20 choose 5, 0.08 to the 5th power, 0.92 to the 15th power. Which is going to give us a probability of 0.0145. The second problem is, what is the probability that all of the computers work? So part A was 5 did not work. B is going to be probability that all work. So now here's the thing. You have to actually, again, this is where the success condition really comes into play, because our probability P is for computers not working. So there's really two ways you can do this problem. If all the computers work, how many don't work? Probability that 0 don't work, meaning we're doing probability of 0. So you could do this, probability of 0, which is equal to 20 choose 0, 0.08 to the 0, 0.92 to to the 20th power, which of course, anything choose 0 is 1. Anything to the 0 power is 1. It's just going to be 0.92 to the 20th power. Or your other approach is you could flip the probability, right? Because if this is the probability of not working, this failure rate for that condition is the probability of a computer working. So you could say, if you're going to use probability of 20 working, this is going to be the probability of getting 20 successes where we flipped P and Q. So in this case now for this one, P is equal to 0.92 and Q is equal to 0.08. So this will then end up being 20, choose 20, because we have all of them working. Our probability of finding a working computer is 0.92, and this is going to be to the 20th power. And our probability of finding a not working computer, 0.08 to the 0 power. So again, this goes to 1, this goes to 1, and look at that. It's 0.92 to the 20th power. Because by changing what our success condition is, it actually ends up being the exact same problem, right? Because that's what these probabilities represent. Your probability for the first one that we did was probability of finding a not working computer. Well, we had 20 that didn't not work. We had 20 that did work. We had 0 that didn't work. For flipping the problem around, we're saying what is probability we find 20 that do work? By doing that, our P had to be the probability of finding a working computer, which was that 0.92. So we had 0.92 to the 20th power, 0.08 probability of not working to the 0 power, because we had none that didn't work. And then we were choosing 20 working computers out of 20. And you'll notice that they get the exact same answer, which will be equal to 0.189. Or problem C. What is the probability that none of them work? So again, this is one you can do two different ways. You could do the probability of finding all failures using this original probability of finding a failed computer, or you could kind of do the approach we did before. If instead of finding 20 working computers, you could say what's the probability of finding 0 working computers. So if none of them work, easiest way to do it, I'm going to go back to our original probability of success, which is finding not working computers. Probability of 20 is going to be 20, choose 20, 0.08 to the 20, 0.95 to the 0. This is going to go to 1. This is going to go to 1. You should do 0.08 to the 20th power, which is going to be some really tiny number. We're just going to say it's around 0. For problem D, it's actually two parts. We have at least 18 work and at most 2 don't work. So I'm going to say not working. So again, this is where you have to really keep track of what is this probability of success telling us. So if we want at least 18 work, so probability that x is greater than or equal to 18, this is for working. This means this is the approach where we're going to have to use P equals 0.92 and Q equals 0.08, in which case it's just going to be probability of at least 18 means greater than or equal to, which same thing as saying probability of finding 18 working computers plus the probability of 19 working computers plus the probability of 20 working computers. You could have also looked at not working computers, but if at least 18 are working, then you'd have to consider how many are not working. Well, if 18 computers are working, that means that you have 2 computers that are not working. If 19 computers work, that means you have 1 computer that doesn't work. And if 20 computers work, that means you have 0 computers that don't work. So if you do not working for this one, it would have to be the probability that x is less than or equal to 2. You would have to consider how many computers are not working. So 18 work, 2 don't work. If 19 work, 1 does not work. If 20 work, 0 do not work. So in this case, this would be the probability of 0 plus probability of 1 plus the probability of 2. The second part of the problem is, what is the probability at most 2 are not working? So at most means less than or equal to 2. That's this one. And of course, like we said, these will actually be the exact same conditions, right? If I plug in these two sets of values into my binomial, let's do this first one. It's going to be, probability of 18 is going to be 20, choose 18. Now, my probability of success for this one was 0.92 to the 18th power, 0.08 squared, plus 20, choose 19, to the 0.92 to the 19th power, 0.08 to the 1 power, plus 20, choose 20, 0.92 to the 20th, 0.08 to the 0. Now, if I do this one, probability of getting a 0, remember this is where P equals 0.08 and Q equals 0.92. This is going to be 20, choose 0, 0.08 to the 0, 0.92 to the 20, plus 20, choose 1, so that's this one, 0.08 to the 1, 0.92 to the 19th power. And then the last one, probability of being a 2, so it'd be plus 20, probability of, rather the 20, choose 2, 0.08 to the second power, 0.92 to the 18th power. Now, if you look at these are going to be the same. Remember I told you about when we were doing combinations that n choose 0 and n choose n are both equal to 1. N choose 1 and n choose n minus 1 are equal to n. And every step you go in, they will be the same. So in this case, 20 choose 18 is the same thing, because it's 20, 19, 18, it's third one in, it's the same thing as 20 choose 2, 0, 1, 2. So these two combinations are the same. 0.92 to the 18, 0.08 squared. These two are going to be the same, because 20 choose 20 is 1. 20 choose 0 is 1. You got 0.08 to the 0 power. You got 0.92 to the 20th power. And then, of course, these two are also the same, because 20 choose 19, that's n minus 1. 20 choose 1, that's going to also be, these are both going to be 20. 0.92 to the 19th power, 0.08 to the 1 power. So if you actually look at it, they're calculating the same thing, whether you go from a working or not working point of view. And then, of course, if you look at the slides, you can actually see how we set these calculations up, just like we did. Now that we've talked about how to calculate binomial probabilities, let's talk about how do we actually graph these binomial probability distributions. So the first thing is you want to place your R values on your x-axis. So these are going to be your R or X values. On your y-axis, these are going to be your probabilities. So this is going to be your probability of R. And then from there, what you're going to do is at every R value, which remember, R represents the actual outcome. So let's say that we're rolling 2 dice. Let's think about what the outcomes of 2 dice would be. If I'm rolling 2 dice and I'm looking at the sum of the faces of the dice, I can get a 1 and a 1, which is going to give me a 2. So let's say that X is equal to, it could be 2. If I get a 1 and a 2 and a 2 and a 1, those are ways that I could get a 3, I could get a 4, all the way up to a 12. So let's say that I wanted to graph this. What I would do is at R, I would put a mark for each of these. So I'm going to put 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Something like this. And then what we are going to do is on each of these R values, you're going to go out, just like we do with a histogram, half of the distance between them. So in this case, because you have an interval of 1, right, from 7 to 8, 8 to 9, that means that 7 is going to be from here to here. And then you are going to draw a rectangle up to whatever probability that that R outcome has. So in this case, we have 1 over 6, 2 over 6, 3 over 6, 4 over 6, 5 over 6, and, 36. These are all over 36. right? There's 36 possible outcomes when I roll 2 dice because it ends up being 6 times 6, so there's 36 total. So for 7, what I do is I go and I draw my rectangle up to 6 out of 36. Then for 6 and 8, same idea. You would go start at your point 8, you would go out r plus or minus 0.5, and you would create your interval. So this one would be from here. This one would be to here. You do the same thing for each of them. So in this case, we have and then last one. And this is how you would draw a binomial histogram, right? Same idea as drawing any other sort of discrete probability histogram. You have your actual R values or your discrete outcomes in the bottom. On the y-axis, you have your probabilities of success. Around each R value, you go out plus or minus 0.5, so that whatever gap you have, you take half of it, you take to the right, you do half it to the right, to the left, and then you create a rectangle up to that probability point, that whatever it's worth. And then you just put that rectangle and you do it for all of them and you've got your graph. This will give us our relative frequency histogram. Now, a couple notes on graphing these binomial graphs. If the probability of success is 0.5, you are going to get a perfectly symmetric graph like I tried to draw here. Now, of course, mine, I'm freehanding it, it's not great, but if you have a probability of 0.5, and we take the expected value, which is n times p, no matter what your n is, it's always going to be the middle value. That's going to be your most likely outcome. And then every one you go out from there, you go down by the same amount. Because my probability of success is 0.5, which means my probability of failure is 0.5. So an example of this would be, let's say that I have 10 trials, and my probability of success is 0.5. Then if I did my expected value for a binomial is n times p, which is going to be 10 times 0.5, which means that the most likely outcome is going to be 5. If I were to go one out to the two directions, this would be the same thing as saying, okay, I want to find the probability of 4. I want to find the probability of getting a 6. If I wrote my binomial probability, this would be 10 choose 4. This one would be 10 choose 6. Because my probability of success is 0.5, this would be 0.5 to the 4th. This would be 0.5 to the 6th. My probability of failure, though, is also 0.5. So if I have 4 successes, that means out of my 10, I have 6 failures. If I have 6 successes, that means out of my 10, I have 4 failures. Well, 10 choose 4 and 10 choose 6 are the same, because like I told you, they're going to be going down equidistant. But also, this 0.5 to the 6th power and this 0.5 to the 4th power are the same, because you have a probability of success that is the same as your probability of failure. So if your probability is equal to 0.5, you will have a symmetric histogram for your binomial probability distribution. If your probability of success is close to 0.5, it's going to be almost symmetric. The more it is to the left of 0.5, the more left skewed it's going to be. The more it's to the right of 0.5, the more right skewed it's going to be. So if you have a probability of 0.1, which is very far to the left, you are going to have your highest value. Again, if I have 10 trials, would be 1 outcome is what I would expect. Then your highest value would be on the left, and then it's going to go down the further you get from there. If I have a probability of something like a 0.92, it's going to be way up here. I'm going to expect more outcomes, right? If I have 10 trials, then I would expect on average the outcome to be 9.2 successes. So around 9 successes. And the further I get to the left from there, the lower your values are going to go. So if you have a probability that is at 0.5, it is perfectly symmetric. If you have a value that is close to 0.5, it's pretty symmetric with a little bit of skew. If you have a value that is very close to 0, you will have a left skewed graph. And if you have a value that is close to 1, you will have a right skewed graph. Now let's do an example where we're going to put it into a word problem like we might actually see when we're using the binomial probability distribution. So it says, when Hughes Corp company is purchasing 5,000 components from a manufacturing plant, it applies this sampling plan. By randomly picking 5 of the components, they will accept the whole lot if there are less than 2 defective parts out of the entire lot of 5. If the manufacturing plant claims they have a 5% of their production may be defective, what is the probability that the Hughes Corp company will accept the whole lot? So we're saying if I were to take that sample of 5, based on the company's projected faulty rate, what is the probability for my sampling plan that I would actually accept this entire lot? So first things first, let's look at what information we have. Well, we have N equals 5 trials, because those 5 that we grab from our sample, where we're going to try to say whether we accept the entire batch or not, you could think of these as binomial experiments, which is to say the first component, it has 2 outcomes. It works or it doesn't work. Second component, 2 outcomes, works or it doesn't work. And you're going to do that for all 5. The company's probability of a fault, which is what we're looking for faults, is 0.05, right? Because 5% would be 0.05, meaning that our probability of not finding a fault in any given part is going to be 0.95. And we're looking at what condition would cause us to accept this batch. Well, it said that we would accept this batch if there are less than 2 faulty parts. So remember, less than 2 means what? It means less than or equal to 1, because that 2 is not included. So it's the probability that our number of faulty parts is 1 or it is 0. So we're going to actually be looking for what is the probability of getting 0 faulty parts plus the probability of finding 1 faulty part. So now setting this up using our binomial probability, this is going to be N choose R, so 5 choose 0. Probability of success, 0.05 to the 0, times probability of failure, 0.95 to the N minus R, or in this case, to the 5th power, plus 5 choose 1, 0.05 to the 1, 0.95 to the 4th power. Now for this first one, 5 choose 0, anything choose 0 is going to be 1, anything to the 0 power is 1. This is going to be 0.95 to the 5th power. The second one, 0.05 to the 1 is just going to be equal to 0.05. 5 choose 1 is going to be equal to 5, so this is going to be 5 times 0.05 times whatever 0.95 to the 4th power is. So in this case, it would be 0.7737 plus 0.2036, which is equal to 0.9773. Now, there's another part to this problem, though, because now, let's say that we found 97.73% of the time, we would accept the batch if they actually do have a fault rate of 0.05. So 0.9773, that is the probability that we would accept the entire batch based on this information. Well, what about if we wanted to know, we accept the whole batch and there were 5,000 total in the batch. So for the second part of the problem, we're looking at the entire batch. N equals 5,000. And now we want to know is, we've accepted the batch, what is the number of products, whatever they are, that you expect to be faulty? So this is our expected value. Based on having a fault rate of 0.05, and we have 5,000 products, this means that our expected value is going to be, if you remember for binomial, it's N times P, it's going to be 5,000 times 0.05, which is just going to be equal to 250 faulty components. What about our standard deviation? Well, if you remember, variance is N times P times Q. Standard deviation is sigma equals the square root of N times P times Q. So we just plug those values in. We have an N of 5,000, we have a P of 0.05, and we have a Q of 0.95. And we take the square root of all of those multiplied by each other, which means we get 15.411. What does this actually mean? Well, this means that of those 5,000 parts, let's say that this is a recurring shipment that I get them every week. That means that every time I'm going to have some faulty products because they have a 5% fault rate. On average, I would expect the number of faulty parts to be around 250. The standard deviation, think about the empirical rule, tells me some distance that we should expect them to fall within that amount, right? Think of the empirical rule. The empirical rule said if we had a normal distribution, that we would expect 68% of the outcomes to fall within plus or minus 1 standard deviation. We would expect 95% to fall within 2 standard deviations, and we would expect 99.7% to fall within 3 standard deviations. This is actually very important, and we will talk back more about this in chapter 5, because if you actually look at the fact that we wrote that the expected value is equal to mu, and we've been writing the standard deviation as sigma, well, binomials don't use mu. They don't use sigma. These are actually approximations that later on we will use to say that if we have a large enough sample size, that we actually can use a normal distribution to represent it, right? If you remember my graph, something like this, we're basically saying something along the lines of, if I have this binomial distribution and I've got a large enough data set, I can approximate it by using a normal distribution. And this is why, if I have enough data, this kind of idea of it holds. It's not exact, but 250 is the average number of faults I would expect out of this batch of 5,000, right? So let's say this is my mean. Mean is 2,500. And I would expect 68% of the data, let's say it's to here and here, this would be plus or minus 250. Plus or minus, well, I'm going to round it to 15 just to make the numbers easy. So this would be from 250 minus 15 would give us 235 up to 265. And we would expect about 68% of the shipments to have faults of 235 faults to 265 faults. If we were to go to 2 standard deviations, this would be to 220 up to 280. So 95% of the time, I would expect the number of faults to be between 220 and 280. And then you could do the same thing with 3 standard deviations. Now again, this is not exact, because if you remember, our empirical rule is for when you have a perfectly symmetric normal distribution. So we actually would have some checks we have to do before we do this, which is why we'll talk more about this in chapter 5. But this is the idea behind it. So the last thing I want to note, though, is for a binomial distribution, it is unusual for the number of successes R to be more than 2.5 standard deviations away. So basically, there's a certain kind of cutoff, about plus or minus 2.5 standard deviations, where if we have values that fall out there, they're generally considered an outlier. Doesn't mean that they're wrong, it just means that they are unusual outcomes. So this means that if I start getting numbers of faulty units that are below 200 or above 300, actually, well, technically probably about 290 and beyond 290 and probably beyond like 215, 210, if I get a number of faults that is outside of those ranges, it's probably not a very common thing. Like I wouldn't expect to get a shipment that's going to have like 23 faults. Just like I wouldn't get a shipment, I wouldn't have expected my 5,000 to get like 340 faults in them, right? So the further you get away from that mean, the less likely it is to occur. And generally, we consider anything outside of 2.5 standard deviations to be an outlier. I'm going to do one more example, and then we're going to be done with this section. So example 7 says, a quality control engineer oversees testing whether 90% of the DVD players produced by his company conform to specifications. To do this, the engineer randomly selects a batch of 12 DVD players from each day's production. The day's production is acceptable provided no more than 1 DVD player fails to meet specifications. Otherwise, the entire day's production must be tested. So basically what they're doing is they're testing a sample of 12 DVD players. If no more than 1 of them are faulty, they will pass the entire batch. If more than 1 of them is faulty, then what they would do is they would have to go out and actually test all the individual DVD players, which, by the way, this is actually part of like how they would do things with quality control. They wouldn't have it to these numbers, but it would be this sort of idea. You sample the products, you see if you get above a certain fault rate, which may indicate you have a faulty system that's making them, in which case you would actually have to go and test all of them. What is the probability the engineer incorrectly passes a day's production as acceptable if only 80% of the DVD players conform to specifications? Okay, so this means that we are looking for the probability that we get no more than 1 faulty DVD player. That means that we are looking for the probability that our x is less than or equal to 1. No more than 1 faulty. It says that we have an 80% that conform to specifications, meaning 20% don't. So this probability we're looking at, you have to determine, are we looking at a probability of finding a fault, or are we looking at a probability of finding not fault? So in this case, we're looking for the number of faulty units. So we want 0 faulty or we want 1 faulty, meaning our P needs to be the probability of finding a faulty unit, which in this case, because 80% of our products fall into specification, that means that 20% don't, or P equals 0.2, in which case Q is equal to that 0.8. These are the DVD players that meet the specifications. So now what we're going to do is we're actually going to solve our problem. So we have probability X is less than or equal to 1. This is the same thing as saying that I have the probability of finding 0 faulty DVD players plus the probability of finding 1 faulty DVD player. So doing this, this is going to be n is 12. So n is 12 choose 0, 0.2 to the 0, 0.8 to the 12th power, plus 12 choose 1, 0.2 to the 1, 0.8 to the 11th power. And then when you calculate this, you will find that we have the probability that this engineer would accept the entire day's batch and we don't have to go test them all is going to be, or probability of finding less than or equal to 1 faulty products is going to be 0.275. So that means that the engineer doing this is only likely to actually accept, without having to test all the batch, about 27.5% of the time. So that is it for our binomial probability distributions. Just remember, whenever we're doing this, that there's a lot of assumptions you have to look at, and you will have to kind of use these assumptions sometimes and the way problems are worded to differentiate between what comes in the next section, which is geometric probability distributions. So remember, we have n set number of trials. Every trial has 2 possible outcomes. There is a set probability of success P, and when you put all of this together, when you sum up all the possible probabilities, they have to add up to 1. Okay, so this is like the kind of stuff you have to think about when you're doing a binomial probability, because again, we are going to have some similarity when we get to the next section, but you will be able to get some difference. The last thing I wanted to remind you of is that your random variable X, when you have a binomial probability, is from 0 up to n. And the key part here is the 0. That's going to be something very important compared to next section. Thank you for watching. To continue learning, click the linked video here for the next lesson. If there's a topic you'd like me to cover, let me know in the comments. Don't forget to subscribe, and I'll see you in the next video.